Yeah, the subject is what kind of security improvements we can do with the link editor, which is obviously used to produce every executable we are using today. So briefly, what loaders and linkers do. Well, in the old times, it was two separate programs. There were loaders that were actually loading the binary in the memory, and then there were linkers, which were composing the binary out of a bunch of object files produced by assemblers or hex editors, whatever. And over time, the format of the binaries and the memory layout became more complicated than it used to be and more subsequently vulnerable for various security attacks, well, exploits. And today, more or less, everybody uses the GNU binutils that includes the linker, where in the older times, every operating system had its own linker because the binary format was not really that common between different vendors. Some used A out, some used B out, some used SOM, and a bunch of other funny formats. But later, as part of the binutils projects, the linker evolved that supported all those old formats, and then later everybody uses ELF basically. But what would be the reason not to concentrate on the GNU linker? Basically, from my perspective, the problem is enormous amount of source code that the linker actually composed of. The binary itself, not including the shared libraries, is about 600 kilobytes, where, say, the reference implementation of the dynamic linker from Sun in the 90s was only 98 kilobytes of source code, not to mention what it was in the binary. So initially, I tried to do useful stuff with the GNU code, but the problem is the, again, amount of sources, and every little feature is not implemented in one place. It's spread out over billions of tiny little functions all over the source tree, and it's really hard to figure out even how things work, not to mention to modify them and keep working. And as a side effect of this huge source code is, for example, that all the binutils, they react differently to a broken binary files. If you have a binary file that has broken structures inside, for example, a read-elf utility would crash and core dump, and an M utility from the same package using the same BFD library, which is the backend of all the GNU binutils, would display you all the symbols just fine. And these inconsistencies in behavior, they also kind of work against the idea of the quality source code. So looking at all that, I just one night figured out, well, screw this, I'll write my own linker, since it's such a tiny little simple program. So the idea is very simple. Throw away any compatibility for all the ancient file formats that nobody uses anymore. Like, well, on Windows is probably the only operating system that doesn't use ELF so far. But everything else is completely ELF. Even super conservative systems like HPX, for example, is ELF now, and it's not SOM anymore. And again, throw away all the features that nobody ever uses.
What about macOS 10 and the object file format?
Isn't it modified ELF also? Yeah, maybe.
The header doesn't look similar in the hex down.
Well, I actually don't even care about macOS X because it's a commercial system. They can do what they want with their shit. And they also ignore all the insane historical behavior which exists, again, as a rudimentary leftovers from things like A-out format, which was a flat file, and even ELF binaries, they're still kind of following the flat file convention that the A-out had, which they don't really have to, but it's kind of convenience over time. So if you want to check out the sources when you're bored with me talking here, you can check out in the Git mirror repository there, and the tiny URL is just less typing since you cannot cut and paste from here. Yeah, so later I'll talk a little bit about how the current implementation works. Well, basic current sources which you can read there, they work up to allowing to build the whole source tree from OpenBSD, for example, or I haven't tried huge programs, but there are slight problems still, and there are lots of room for optimization, because in the beginning I took just a straight approach to get things working, and it's very easy to do optimization. So far, modifying and adding tiny little features end up with like 10, 20 lines of code, which is very acceptable. And these sources is basically 3,000 lines of code, and probably half of it is just comments and spaces and stuff like this. So briefly, in case somebody doesn't know how the ELF is composed inside, well, we have a little header that describes the rest of the metadata, and then basically we have the actual program text and data and the possibly other stuff, and then the symbol table and possibly debugger information if the compiler generated it ever. So the interesting part also is the relocation data. As you can see, the text and data sections which contain the code and the initialized data from the compiled program. They may have, well, code for sure would have references to other functions and jumps to other locations within functions, which in case we just compile the file with the cc-c to produce just a relocatable object, well, it has to be relocatable in memory in the sense that later we will be composing this object by the linker into final programs. So all of them are initially compiled for unknown addresses. And that's where the relocation data comes useful, where it connects these little addresses in jumps and call instructions in the code to actual functions or labels, which are usually listed in a symbol table. So the relocation is basically two integers. It's an offset in the text or data section and size of the address, because it could be 16-bit or 32-bit address, or it could be just an offset, small offset against the variable. And then, of course, the index in the symbol table to the symbol that it's referring to, such as a function name or a global variable or static global variable. And this piece is also very vulnerable, basically, in the GNU linker. Producing garbage in the relocations really make it unhappy. And there is no diagnostic. It basically produces random, unuseful results. And another part of objects that are used in building programs is, of course, libraries. So in case of static libraries, it's basically sort of like a tar archive, a bunch of object files just dumped one after another. The only tiny improvement over tar is the so-called simdef, which is, well, the name comes from the old, again, A out times in the ELF libraries from as defined by System 5 ELF. It's not called simdef anymore. It's just named slash or double slash. And basically, it's the index of the files in the archive, sort of like we have in the zip file, where you have names of the objects and all the functions and names that are defined there, and offset in the file where the object is. Because when the program is composed and the library has to be scanned for all the unresolved symbols and needed functions and stuff, without the index, we would have to scan the library over and over again, which is a very costly process, because we have to read the parse ELF headers for every object file, which is, in case of libc, even would be like several hundred or even over 1,000 objects, and it would cost enormous time and disk I/O. And again, in the old times, the index was not mandatory, so technically you can say, yeah, my library is small, screw the index, and worked with just scanning the object, but in the modern days it's actually mandatory, and most of the linkers would refuse to use the library if there is no index. Which is, again, I totally ignored the case where the index doesn't exist, which makes it simpler and faster. So then, functionality-wise, a linker basically consists of two parts. First, we have to gather all the information about all the input files, figuring out what objects we need from libraries if they are specified, or figuring out which libraries to use. And for example, in case of shared libraries, there are major, minor numbers on the library, so we have to choose the one that we want to link against. And well, the dynamic linking part, I'm kind of skipping on purpose. I will explain a little bit later why this decision was made. But basically, dynamic libraries, they are not like normal libraries. They are basically one big object file, which is already linked and composed in one solid address space layout. So anyway, once we figured out what the files we want and what are the sizes of all the sections in the files and what are all the symbols that have to be resolved from libraries, so basically that creates one huge index, like a tree, or partially it's one part of it is a symbol table of all the very global names that are involved. Once we have all that, we can figure out where in memory in the address space to put all these pieces of the objects and basically generate the output binary by just copying over all the stuff from the source files into the output, which is historically still called A-out, even though it's ELF. So what is the important parts of the of this process that are relevant to our discussions? Basically, what linkers do, they take the order of the object files and libraries as specified on command line and place them in the memory, allocate the address space for them sequentially and linearly, starting at some certain fixed address or even random address. It doesn't really matter in this case. So, and the same with the libraries. The libraries are scanned in the order that is required by the undefined symbols from the object files, and again by the order they are specified on the command line, and basically that produces almost 100% predictable output layout of the executable file, which is, I mean, very cheap to do, but we will see later that even cheaper we can do better stuff. Yeah, so again, it linearly just stuffs in the address space, and all the sections from different object files, they're basically put together right after another with the tiny little gaps, which are required by basically alignment, such as on the RISC architectures, you have to align to say 4 bytes for the instructions, and certain data types like doubles have to be aligned to 8 bytes and things like this. So linker has to know about it. And then these little gaps between functions or object files in the code usually filled with nope, which is kind of became convenient because on the CISC architectures, nope is usually 1 byte instructions. So if you have to align to 3 bytes, it's easy to do with just 3 nopes. You don't have to think about choosing instructions. Of course, again, on the RISC architectures, that's not a problem because every instruction is, say, 2 or 4 bytes, and it doesn't matter which instruction you choose. And data is usually gaps in data usually filled up with zeros.
What about cache lines on those architectures?
Well, this is kind of artificial optimization, which is you can do yourself by changing alignment in the instructions for the linker or in your code or blah. But functionality-wise, it's not changing anything. Or even worse, I mean, it works on one machine, and on the other machine it might be working much worse than actually even expected on the slow machine. Yep. So evolving from this, what are the typical attacks that are done on the running binaries, basically? usually it's some sort of one pointer overwriting, such as overflowing sort of stack buffers and overwriting the return addresses on the stack, or overwriting pointers in the data structures such as function pointers with the code of external code blob that was placed in the exploited buffer, for example. So there are a number of ways that people figured out to how to fight these attacks. So one of them is, of course, address space layout randomization, such that if we manage to overwrite the return address on the stack from the exploited function, in the good old days where every time you compile a binary and run the binary, everything would be at the same location. Every function would be at the same address, unless you heavily modified the sources, for sure. So if you want to overwrite the address, it's very easy. You figure out what kind of binary the system is running, you figure out where the address is, and you compose the new return address, and there you go, you running the function or piece of code that you uploaded yourself in the buffer without much effort. So since then, people figured out, well, okay, we can randomize the binaries when we load them, which is usually done by the dynamic linker, which means static binaries are left completely unprotected. And there are things that we can do, we'll talk later. So at this point, basically, there are two things that we are interested as an attacker in, is the absolute address or an offset against a function, such that we can abuse the ending of the function that produces us the desired effect, in which case we don't have to upload the code into the target system. We can just upload the arguments on the stack that we want to run the existing function, piece of the function that the program has. And then we use the offset against the beginning of the function to jump to the middle of the function to do what we want. So basically, again, against the absolute addresses, the randomization of the shared libraries help for attacks such as returning to libc. And but the offsets that are used as a offset against the beginning of certain function to abuse the ending is actually completely left unprotected, because technically we can use another exploit to figure out the address space layout by abusing printf format strings, for example. The typical mistake where people don't use the format string, they just put the directly string as the argument for the format in the printf, and the string was supplied, for example, from the user input. In which case we can fish out the location of the libc functions, in which case the offset is easy to figure out and it will be constant almost for any even the rebuilt system. So this is what basically people do today. Separating code and data. Well, I mentioned PDP-11 there because in the late PDP-11s, well, not so late, since 45, I think, they actually had completely separate code and data. So if you have a pointer on the stack that you're trying to exploit, first of all, you don't know if it's data or code, because it's two completely 16-bit address spaces, which are separated just because of the function. So in modern days, usually it's done in the TLB by using the non-executable permissions. So the previous work that was done in, say, OpenBSD some years ago is to keep only the necessary executable parts actually mapped executable and keep the rest of the system, rest of the address space non-executable and preferably not writable if possible. This basically helps one defeat the attacker who uploads the code and tries to execute it, because to execute it he has to call mmap, which we can get around and basically abuse the function in libc that ends in the mmap or mprotect to modify the existing address mapping. And this is not very well protected because, again, the offsets are basically constant. So another useful part is the randomized stack location, which is usually done by just jumping the stack pointer before the execution of the binary with some random value, which is up to, I think, 256K, which basically gives us about 16 bits of entropy for the stack pointer. And again, the shared libraries are mapped randomly by the shared linker. I don't think most of the operating system actually up to doing this even today, even though it's like 10 years since this has been implemented. The tricky part on i386 is the absence of the non-executable bit, where basically we have to split the address space in two parts and keeping the lower part executable and upper part not, by using the segment registers, which is, for example, doesn't work on the AMD64, but luckily we have a non-exec bit there. And another randomization also is randomizing the malloc memory, which is, again, helps with absolute pointers by fishing the dynamic data structures and the, say, function pointers, for example, in data structures to override. So randomizing section addresses, such as data or code, only gives us about 16 bits of entropy. This has been basically proven to be not a serious protection. And by brute force, assuming the binary doesn't crash by us trying to guess the addresses and trying to run the code that we want to run instead of the normal program flow, this on a fast machine and reasonable network connection would take us about a couple of minutes. So this is basically not a serious protection like this. And again, the randomization done by the shared linker, which uses a funny system called mquery to basically obtain the address space layout for the new binary to figure out where is the executable part and where is not executable part. This is sort of on the i386 and the PowerPC related. Most of the other architectures, they have per page execution protection. And then mmap basically does the actual randomization job by figuring out the part of the address which would be random. But this also has a problem, which is the data is always at a fixed offset against the code. Well, if we speak about i386, which basically means if we figure it out, either some function address or some global variable from the library, we already know where the rest of the library is, which greatly simplifies the whole guessing process. And basically the ordering of the actual objects and libraries in the memory by the linker, they completely unrandomized, therefore it doesn't give us any help. So the starting addresses are usually sort of page aligned, which means only the upper from the page address 16 bits are randomized and the lower 12 are usually the constant, more or less, over the whole binary, which reduces the guessing space. And another interesting measure to improve more the randomized dynamic binaries is randomizing the actual binary, because all this randomization that we were talking before was only done to the libraries. So if we have an actual binary, it's still at a fixed location, and guessing addresses is very easy because it's always at the same place. And to defeat that, there is a position-independent executable approach, which is on most of the actually RISC architectures, it costs nothing because they don't usually operate on the immediate pointer addresses. They usually operate against offsets, which makes dynamic code much easier. But on architectures like i386, it usually embeds the addresses inside the instructions. So calls, for example, and long jumps, they are usually absolute jumps against the program, not against. Anyway, and all these addresses for the binary itself would be fixed, but making them dynamic actually costs about 10% performance. But if we say we are running this super duper 100 core 0 and 3 gigahertz machine, we probably don't care about the overhead. So basically, what we can improve on the existing linker approach and address space layout. First of all, we can, while at the time of linking the program, we can randomize the order of the objects being loaded from libraries and as they are specified in the command line. There is one tricky exception is the startup code that every binary has that finishes sort of the address space setup as done by the kernel, but it's usually and also executes constructors and destructors if those are specified in the code. So, but this is two tiny little objects which are loaded, one in the beginning of the program and the other one has to be in the end to preserve the pointer accumulation for the constructor destructors. But the rest of the objects could be completely randomized, which means by simply relinking the program, we can achieve easily another 10 to 12 bits of entropy for the addresses, which increases the search address space much more considerably, and plus to that, increases the probability of program actually crashing when the wrong address is guessed, because it's possible that the code that they will be trying to guess will be something completely different from what they expect it to be. And another thing, we can randomize the starting addresses for all the sections in the binaries beyond the level where what the shared linker does, because basically we can, unlike all the linkers that exist, exist today and just load the pieces of the object file sequentially after each other, we can simply insert gaps, and gaps that are also bigger than the page. Because again, unmapped address space doesn't cost anything. And unlike in the old times, we have the whole 32-bit address space, unlike it was, say, on Vox in the old times, where we had only a fraction of the 32-bit address space. So we had to pack our binaries and save every tiny little page. And today we can just throw away a couple of pages and say, yeah, well, who cares? Which is, again, a higher probability that the exploit will crash the binary instead of keep it running and guessing. And next restart, we will most likely have a completely different address space layout. And another thing, why do we have to fill the gaps in the code, for example, with knobs? Because this essentially provides the attacker with the extra slack at guessing addresses. Because if he doesn't hit the address exactly, he hits the knobs and then just slides down with what they call a knob slide, and ends up at the same code where he would end up anyway. So instead of filling with knobs, we can as well fill with horrible instructions like overflow interrupt, which is usually not used by any existing Unix operating systems. Well, integer overflow. Or with privileged instructions like halt or any other horrible stuff, and make basically the kernel kill the program instead of keep it running. And again, next restart, it will have different address layout. So another hard part about dynamic binaries is the global offset table and the program linkage table, which are used to access the objects from the library by the binary. Since the library could be located at any funny location, the binary itself has to have a meaning to access the objects from the library in a consistent manner. So for that, it's basically well, PLT could be a pointer table on some architectures, and on some it's tiny little code which simply has jumps which are fixed by the dynamic loader. But basically it's more or less a pointer table which is filled by the dynamic linker with the pointers to all the objects in the shared library. And then the binary uses this table to do double indexing to access the data. This is basically the stuff that Sun came up with in the 90s and everybody using today. And there are, there are performance problems with it. So on average, it's about 10% performance problem, performance hit, and on the Perl, for example, which is, or Python, or who else is doing this horrible stuff, where the whole program is basically a library, and the binary itself is a 1 kilobyte tiny little function that all it does is calls the interpreter, which is in the dynamic library, which means the dynamic library itself has to follow the dynamic library convention. And due to awesome, for example, Perl design, which is consisting of billions of tiny little functions calling each other through pointers and blah, 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 this actually essentially kills the machine under any serious load. It's a complete denial of service to run dynamic Perl on any kind of production machine where the Perl scripts or whatever programs are used for some kind of network applications. Well, which people do a lot, apparently. And another problem is that, one, we have to keep both tables, first of all, read-only, and second, the code must be non-executable, and well, POT has to be kept executable. The problem here is that a common approach to improving the dynamic linker performance is to not fix the whole table at the loading time, but do it on demand. So every time we access the object from the library for the first time, it goes, figures out the offset for the table, fills up the slot, and then goes on. The problem here is that in the old times where nobody cared how these tables are mapped and how can they be used for exploiting, it was very cheap because no system calls were involved. All they had to do is do one tiny little hash table lookup, figure it out the address, punch it into memory, done. But if we keep these tables, which is called the writable or executable approach, which was implemented also in OpenBSD several, or even almost 10 years probably ago also. Anyway, then fixing every slot in these tables actually causing 4 system calls, which is also enormous overhead. And basically for typical network daemons or network applications, again, even worse if they're written in Perl, or something like Perl, or for example, Python, that basically we have to, instead of fixing all the stuff in the beginning when we load the binaries, we end up calling all these crazy system calls for every function for the first 10 minutes of binary running, and that also causes enormous performance problems. And of course, the obvious benefit from dynamic binaries, as we saw before, is that we can randomize the binaries and the libraries that the binary uses. And of course, we can randomize with the position independent executables. We can even randomize the binary. But nobody said that we cannot make static binaries, which are one solid binary, including all the libraries and everything, also be kind of dynamic by behavior. So one thing that basically I implemented in the linker that I have is, as I mentioned before, is shuffling all the objects, all the functions and the objects in the file, therefore providing even more entropy to the address that the normal dynamic libraries provide. And again, shuffling the sections. And the funny thing is that in the old times where people didn't have memory management units, all the programs ran in the same address space. So the problem was to execute the program every time it had to be relocated to a new address space. So we had to figure out where is the empty piece of memory, fix all the addresses in the binary, put it there, and run it. So in the old times, it was a necessity because there was no virtual memory. So then people figured out, well, we can use the separate, completely separate address spaces for every binary. So they thought, okay, since we have a fixed address space completely owned by one binary, we don't have to load the whole binary every time fixing all the addresses. So let's load it at a fixed address, which bites us back on the ass because now all the addresses are predictable. So we sort of lost a little feature which was before, which is the binary, which could be randomized at load time. So as part of this linker work, inside the linker there is another kind of over-optimized tiny micro linker, which is used for one special case that exists on all the BSD systems. The library, well, actually Linux does it for kernel also, but on BSD systems it's done for library objects. Every library object is preloaded, pre-linked after compilation to purge all the local symbols that are not relevant or never be referenced from outside, to reduce the size of the symbol table and therefore improve the later program linking time. So to optimize this tiny little case, which is linking one file by basically not fixing the addresses completely in the file, but just getting rid of the symbol table entries and relocations, I wrote one tiny linker, which is actually a couple of hundred lines function, which all it does is just modifies the one object file, which is assumed to be input and output, and just throws away the symbols and everything. But one repercussion of this strange optimization is that this tiny linker could be used now as a good old timer loader. So every binary, instead of going through the whole hustle of dynamic tables and the dynamic loading and everything, which has enormous overhead right now. Instead of that, we take a tiny little overhead by basically doing the good old school dynamic loading of the whole statically linked binary at the runtime. So when we run the program, what it does, it goes through all the addresses, it figures out the random locations for all the segments and functions and whatever. And which ELF, again, allows us, because ELF has all the metadata in it, describing all the pieces and the chunks of the address space. And basically, we can do it at the runtime by fixing all the addresses once, and then every time we run the binary, we have completely randomized address space, which is, from the point of view of running the program, which is the case for our basically exploited applications, which are the network daemons, or say browsers, or shell command line shells and stuff like this, which is running forever. So there is no point in taking all this effort into maintaining dynamic linking structures and everything, because we can fix it once at the load time and run it for a week or until it crashes, and still have the whole address space randomized without any overhead caused by the Sun approach for the dynamic linking. So yeah, this is what it allows us to, well, another side effect of having a tiny little linker as part of every binary, which again, we can, after we loaded the binary, we can even throw away these couple of pages that this code occupies and save some memory. So there is another funny thing we can do, is we can define dynamic locations, such as the system call entry points, which is a topic for another talk I have on Monday, I think. And basically that way we can make it harder for attacker to use system calls from his own code exploit code that he uploaded up there. But it's bigger part of the another talk. And another completely wacky idea that we can do, we can have binaries that are moving themselves in the memory semi-constantly. Because we have the binary, we have all the information that is required to move it or map it anywhere in the memory. So if we design the binary in a way such as like typical interpreters do, basically they use no global data, they have basically code, and all the data is dynamically allocated during parsing and running program or whatever performing the function. So if we don't have any data pointers in the data section, which is easy to do if we write our own program, we just have to remember not to store pointers in the global variables or function pointers. So if all we have is basically code to relocate, what we can do is once in a while, what, for example, Apache does. It does re-exec after, say, blah requests. The reason is, well, in old times was the memory leaks, or in the modern times, if you use modules, PHP and stuff, you have to re-exec because they leak memory. But in the old times, the idea, well, in the new times, the idea is that by re-execing, you re-randomizing the address space constantly. So if the attacker started trying to exploit and figuring out addresses on one of the, say, Apache servers, eventually it will re-exec and he has to start over. So instead of re-execing, which is quite costly operation from the whole system perspective, besides occupying the whole kernel time and all this horrible stuff, what we can do is we can re-randomize the address space ourselves. Of course, we cannot re-randomize the data that has been mallocked already, but we can shuffle the code any way we like. So say every 5 minutes we go and we like move one function somewhere else and then fix the addresses. And then next 5 minutes we move some other piece of code somewhere else. And we just keep shuffling around. So basically or if we have some idea that, oh shit, they're trying to break in because there is this typical pattern, whatever, if we have some kind of IDS-minded Apache, we can say, oh, okay, they're trying to break in, let's shuffle the stuff around and make it harder for them. Yeah, we can do like the good old gated did. Gated in the old times, in the 90s, because it was programmed too big for any normal human to debug. They figured out, well, screw debugging. They made a SIG-fold handler, SIG-sec handler, which they would figure out, oh, wait a minute, where did the sec-fold happen? Oh, we were trying to update the internal routing table view. Well, screw it. Let's flush the routing table and redo it instead of restarting the whole gatey. So we can do the same thing here. Every time there is a sec-fold, we say, okay, let's shuffle the stuff around and see if it works better this time. Of course, if we know data locations where we store the function pointers, we can even do that and modify the function pointers if we know that. Of course, that would be hard with, say, C++ programs because it's all somewhere we don't want to know where it is. But this is, of course, one second, a questionable idea. It's kind of wacky, just kind of funny, but I'm not actually sure that seriously improves security, but I think it would be really funny to have stuff like this.
Yeah, one objection to that, because if you start shuffling code around, you have to make all the pages writable.
No, you map them because you know the file. Well, the way binaries are executed today, nobody reads the stuff in the memory. They just mmap the file in the memory.
Yeah.
So then the page fold takes care of loading the pages. So if you want to move the code around, we just map it somewhere else and fix all the references to the new code location and unmap this page. So anytime somebody will hit it, it will be paged in from the binary. Because we know the binary. When we execute, we can just simply open the binary. So even somebody removes it, we can still have the code and data, whatever else from the binary. And all the relocation info. We don't have to keep in memory. We can read it from ELF when we want it.
The references, we have to fix them. And
Yep.
to do that, we need to write to the code. If there are calls inside the same
Yeah.
field or something.
Yeah, for sure.
You have to pay
Yes,
multiple-
there is a problem, yes. So,
To accept this problem, why keep a double interaction? Why not just have a dummy function which would patch itself to the original version? So
well, that's what basically the dynamic linker does now, and it actually costs a lot. So basically, if the whole idea of doing this kind of morphing executable is, it would be much cheaper than doing it with the dynamic linker. Because with the dynamic linker, it's even easier to do because all the function references go through the indirect table. So all we have to do is just fix the pointers in the table and keep remapping the code around. But the overhead of the dynamic binary is actually quite huge. So if we want to save the planet, conserve the power, we want to try to make programs use less CPU, not more CPU. And stuff like this. Well, yeah, this is basically the end. So any questions?
How much time does it take to more things on running binary?
Well, basically, another counter argument to it, it's not scalable, because to move one page of code, basically we cannot estimate the cost because we don't know how many pointers it has in it, in jump and call instructions. So technically we can say, yeah, worst case, we have to write 4 kilobytes of memory, well, which is not true because there has to be some code in there. So say we have to write, for every page, we have to rewrite half a page to fix the pointers, which is, of course, kind of big work, but then again, morphing is just wacky idea. It doesn't have to be implemented necessarily. And doesn't necessarily, well, first of all, for 90% of the binaries, doesn't make sense. Because one, they're not taking user input, so they're not exploitable by the user.
Yeah, because I get this idea right. You talked about the maybe APG with the IDE.
Yep.
And the come an attacker and we remove the binary, and it sounds like
Yeah, it's kind of DOS because he starts abusing CPU. That's why, again, it has to be figured out for every single case. It's like antibiotics. There is not one antibiotic for everything. You have to figure out which one kills what and use it proper or not use it. But again, for things like, for example, shell interpreters or any kind of interpreting languages like Perl or Python, that would actually be easy to implement because they usually don't use much of the data section. They might have like constants and stuff, but not necessarily function pointers. So there it would actually be easy to do, but it doesn't have to be triggered by the user actions. It could be done just say every 10 minutes. You?
How far is it implemented? I mean, you said this dynamic movement during runtime you don't have, but we can link static binary that does up on load, randomize its memory there. That's existing, or?
Well, the function exists. There is basically there are a couple of, well, the funny thing is like the whole system could be linked using this linker and it works except for the linker itself. So if I relink the linker with the linker, then there are problems. And debugging is a problem because, again, the debugging, there is something wrong with linking debugging information, so GDB freaks out. So this is kind of...
This is related to the work section.
Yeah, well, another make it harder factor is that the code is compiled also by PCC, which is the portable C compiler, again from the strike from the past. It's stuff that was more or less invented in the 80s and most of the commercial compilers were based on. But then it kind of went away because Berkeley stopped doing BSD and therefore maintaining PCC. But a couple of years ago, what's his name, Rage, anyway, I have a page somewhere. Oh, I don't have anymore. I rebooted. Anyway, but if you Google for PCC, you find it. The pcc.ld1.se, I think. It's at the university in Sweden. And Ragi went and he revived the old source, which is actually based on pretty solid algorithmical ideas and serious research that basically used by all the other compilers also. And most of these special standard compilers that used to come with Solaris, Sun, HPX, and all kinds of System 5 for Motorola systems and the VAX compiler, they used to be based on PCC. And again, the code is, well, the source code for PCC is about the same size as the binary for GCC. And the speed of compilation is about 5 to 10 times faster, and the code quality is basically comparable. There are very special optimizations that are not done right now, but it's reasonable. So again, to make things harder, I compile things with PCC. which doesn't produce dwarf, which produces stops.
So you can't use it in conjunction with
With GDB. No, the code is basically compiler generates assembler. So what you assemble it with doesn't matter. In fact, I'm even using the GNU assembler right now. And so the output object files, they are binary compatible. You can link it against the libraries which are made by GCC or whatever. The problem is the debugging information because PCC generates stubs and GDB by default doesn't parse stubs, which is the old format from before the dwarf times. And yeah, making it do dwarfs, I actually not sure if it's worth it, but maybe later. Because dwarf is really worth on really huge binaries and stuff. Because stubs is composed of the fixed size data structures, which are supposed to describe everything. And that could potentially occupy up to 10 times more than, for example, dwarf would take. But on the other hand, to parse dwarf, you need like 10 times more code than you need to parse the stubs or generate the stubs. So it's a kind of balance between time spent at runtime or debug time and time spent on compiling and generating the binaries, which is actually a big question. What is more important, compiling time or the runtime? Because saving 50% on compile time is very essential. But saving 10% on the runtime, basically, who cares? User gonna get his page in 1 millisecond or 0.9 millisecond. Well, put 2 machines, it's cheaper.
You said you can have high executables because of the runtime performance issues, but then again, all the libraries are already positioned in code.
Yep, and that hits us really bad. On average, when Sun did this work, they said, well, again, that was on Spark machines, which are, say, on average 100 megahertz. So, well, they had multiples up to 4 CPUs, and bigger ones had some more, but still. For them, at that time, at the performance level, 10% hit on average, they decided it's acceptable from the commercial marketing, whatever point of view. But again, nobody used Perl to write Apache web servers at the time. So today, if you try to run dynamically linked Perl, it's basically death immediately. Because all it does redirections, and basically the time spent on useful stuff just goes to 0 very quickly. So that's another problem with dynamic libraries and why I'm basically trying to stick to the decision, screw the dynamic libraries, and do dynamic loading by using this tiny super linker that is part of the bigger linker, which I can move out to the startup code. And basically, there is almost no code modification needed because the way it works now, it fixes relocations to be relative to the start address of each section. So, which basically means offset 0. So we change the offset 0 to a random number, which is the loading address in memory, and just add it everywhere. So the code is exactly the same. There are possibilities to improve the performance of this process. Because if you're loading multi-megabyte binary, which again, why would the network daemon be 500 megabytes? I don't know. But for couple of hundred kilobytes binary, which is reasonable network accessible, some kind of daemon program, whatever, it's not such a big deal to just go and fix all the stuff on a loading time.
What about the performance hit on newer architectures like AMD64 with program counter relative addressing nodes?
Well, it's just bigger addresses, but we cannot get away. Well, on AMD64, we actually can totally get away from doing a lot of relocations by using much more relative addresses, because actually AMD64 ABI encourages using relative addresses instead of absolute addresses, especially for function references. So, and in so-called small memory model, they basically insist on using only relative 32-bit addresses, which means the whole dynamic loading thingy is a complete waste on architectures like this, or on basically any RISC architecture, where everything happens at no cost. You can just use one register as it's used for the dynamic loaded binaries. You can use one register to do relative offsets or PC relative jumps and calls and stuff like this. So today, basically the good old dynamic loading scheme becomes just waste and abuse of CPU power. And again, makes linker much more complicated, because linking dynamic binaries is a different process from linking static binaries, because we don't load the library into the binary. We just have to fill out the table references and stuff, which is stuff not ever done on a normal static binary. So again, it increases code complexity, and as we know, complexity increases bugs, which are creating, again, problems. And then again, for example, the GNU linker dynamically linked is about 600K, but the linker that I have is statically linked is about 130, which includes libc and all this stuff. So basically, it's much smaller code base, which is much easier to figure out the problems in, or simply review for potential problems by just reading the code, where it's really hard to follow in the BFD library, which is Benudils are using, because it's about 3 abstraction layers on top of each other, and each one of them basically hides all the problems in the previous layer. So if you figure out problem in one layer, it's actually potentially creating problem on the next one, because it relies on the broken behavior of the previous one. And it's horrible.
One of the arguments for using dynamic linking is that you can easily fix bugs in libraries and not have to recompile our binaries.
Well, first of all, you have to at least restart the binary.
Yeah.
So as long as you are restarting the binary, you might as well recompile it before.
Yeah, but I think in your model, couldn't you even map from different program files and just kind of statically link in the library as well? So your approach uses the binary and then relocates the binary.
Yep.
The static binary. So you could as well just relocate the static library into the same storage space as well and fix up the differences. Does it work?
Well,
Code only on one.
if you want to update the, say, dynamic library at the runtime, first of all, it heavily depends on how the dynamic libraries are actually versioned on different systems. Because if you do a major change to the library, such as modifying APIs or adding, removing functions, we cannot do anything. We have to rebuild the binary. And first of all, the average user, sysadmin, he is rebuilding or she is rebuilding the library, has no clue what has changed in the library. And basically, the average code practice done in the GNU software, they basically don't care. They change everything, and you have to recompile. So as long as you have to recompile, and as long as you have faster compiler, you just recompile. Of course, we are not talking about things like Mozilla that uses 10,000 libraries, each one of them of billions of lines of code and everything. I mean, if we have to restart Mozilla, the only user who suffers is yourself, who might as well rebuild it before just placing the library. So this tiny little optimization of, let's just call the library and restart the binary and hope it works, could actually really cost you, unless you actually know what's going on in the library. And the reason why you want to do it is when you have a huge library, because you don't want to rebuild the whole system. But again, in the huge library, you have basically zero control over changes that are happening, unless you're actually a developer and following every little commit that everybody does. And if you have a small library, it's easier to simply review the changes and say, okay, we can replace it, but who cares? If it's a small library, we might just rebuild. It's 1 second. So it's kind of chicken and egg problem.
Could you rewrite it as an injector, existing binaries?
Well, basically you have to relink stuff. So all you have to do is use the startup code, which is known as CR0. So you have to take your object files. You don't necessarily even need to file anything. You just have to make sure that, for example, if it's all built from C, C++ or any kind of stuff like this without involving wacky assembler thingies, which, again, if they follow standard ABI, then it's no problem. They are indistinguished from C code. So as long as they all following the same ABI, you can relink the binary against the different CRT0. Of course, doing it for, say, Debian or any kind of Linux is much more work because the CRT0 there does much more different and also different things that it does systems, on any BSD system, for example. So, but theoretic code, the thing is, it's the same ELF binaries, it's the same code, text, data, whatever layout. So all you have to do is just do it, link it with the CRT0, and then it does its job because it knows where the shit is at the time. So technically, it's just a question out how it works on Linux and adopting it. Again, the linker part is dependent of the rest of CRT0. So you can take one function and then place it in a place in existing CRT0, and then it might just work without huge modifications. And again, it doesn't anything special. There are, well, the whole linker is using this library, which is simple, very simple functions to like swap the fields in the ELF structures, so you don't have to write it over and over again. Read the structures from the binary and the little helpers. The whole library is about 10K binary compiled, and you also by other thingies like NM, R, well, runlib for sure, size, strip, all these binary operating thingies. They use the library just because it's easier to just load, use the same function, yeah, give me the section headers, give me the program headers, without thinking where they are and writing exactly same code to do it in every binary, just to say. So the tiny little linker, basically, because it operates on the binary already mapped in the memory, you need to read anything. So all it does, it just uses existing structures by getting offset. So it doesn't even require the magic library for it. So it should be really easy to move. Well, the only difference could be the naming of the ELF structures in the headers. That actually might be because I think the BSD ELF thing is, it's even different in all BSDs. Because in OpenBSD it was written in the 96 or something, but Eric Tyson, I think Eric Tyson, and in FreeBSD it was somebody else, and in NetBSD it had something else, and original BSD from ELF, because it just didn't exist at the time. And then, yeah, Net extended ELF to do ELF on VOX, which never had ELF before. And so I would expect on Linux there are different names for constants and all the defines and structures. So that might be wacky. Perhaps it's easy to fix with the defines or something like this. Or just rewrite it. I mean, there's a couple lines. You can just go and forget about it. You
already said it here from my first time. Did you happen to have a look at LLVM regarding
compiler, you mean? Well, if we talk about compilers, LLVM, same problem that GCC has. It's an emulating compiler, which means time overhead is just by definition insane. It generates the code. It basically generates RTL from source code. And then to generate the assembler, it just runs it in the magic virtual machine. GCC has like Lisp basically in it. Well, sort of. And the LVM has its own stuff. But one, it's C++, which immediately makes it harder to compile. So the compiler itself is already hard to compile. Huge, it's like 30 megabytes or something. And to have one backend for LLVM, a backend for the smallest backend for the LLVM for one architecture is more lines of code than the whole PCC for all architectures that it supports. Again, understanding the code and fixing the code and reviewing the code, it's basically exponential backwards code size. So LLVM is basically impossible for the human brain to do anything about. It's like binary software, it doesn't. But you cannot say anything in the middle. You cannot say, okay, it's broken, we have to fix it. Like, we don't know what's broken. It's millions of lines of code. It's comprehension by human brains. So this is another reason for trying to improve. Well, PCC on i386 is quite reasonable. So at this point, there is kind of one not even major bug, because out of the BSD source tree, it only affects one program. There is one bug that is easy to fix. I just have to do it. And again, it's morally developed and supported by, well, the original, Rage, and there are several other people who work on it also, and it once in a while, and other people. And there is ongoing working more architectures, but basically the idea is to have all the machine-independent stuff work before exploiting it on everything, because potentially that might involve changing functions and changing functionality in the backends, even though every backend 2,000 lines. Well, when you have a compiler which is, the whole compiler is 10,000 lines, you are too lazy to go and modify 2,000 lines. Just because you can modify them, you can actually figure out things. Where in the huge software, you don't care. If you change APIs, well, you cannot verify if it breaks anything or not anyway. With it, see what happens. So yeah, but LLVM, same as GCC, this model of emulating compiler allows to find a whole different class of problems possible with traditional compiler design, such as all sorts of dependencies on the uninitialized variables and stuff, which actually GCC, after all these years of development, this bug as it was in GCC, it still you have two if-else constructs and one local, say, variable we used in both, two if-elses with the same condition. And the variable is used only in the if part or the else part of both ifs. GCC still cannot figure out that that it will complain that this variable is potentially used uninitialized. Still cannot figure out the code flow and see like, okay, we initialized variable in and we use it in another if, but the condition is the same. And therefore, it can be used uninitialized because we always take the same code path in both ifs. So technically, this is exactly the type of code analysis that the emulating compiler is supposed to figure out. But GCC still doesn't. I mean, at the amount of code, I am not surprised why it doesn't figure it out. I think the developers of GCC actually don't. Well, actually, they said shit about people who use GCC. There was a thread a few years ago where Linus was bitching about illegal code generation by GCC, and the GCC people said, "Screw you! You don't know anything programming, and like, shut up and do what we tell you." Which is basically, you care about your variables, you have to declare all of them volatile. Which is basically, why do we need keyword volatile in the first place? Let's just volatile all the time and forget about it. No, the variables that you care about make volatile, and everything else you might. Which is making no sense. GCC is just like project for itself. It's just for GCC developers. Everybody just kind of happened to be able to get something useful out of it.
Could you quickly show the slide with the URL?
URL is easier probably, only 6 letters. Yeah, and the same user bin directories, there are, well, it's a normal source tree basically. There are other utilities that use also with ELF binaries, and for historical reasons, things like R and M, I's and stuff, they also parse A out and ALF at the same time. You can just compare the code if you're interested in this kind of stuff and see how it works for A out, how it works for ELF. And the library is also easy. Instead of user bin, lib/libelf. And there is only one source file there with like 10 functions. Yep. So, thank you. What's next?
Yeah.
Who's